Welcome back, students, to the next session of Basics of Mechanical Engineering, Unit 3, Thermodynamics. So in the last class, we explored some really important definitions such as of systems, surroundings, and boundaries. And then we looked at different types of systems. We looked at the variations of these systems, and so on and so forth. Today, what I wanted to do is to elaborate on these definitions and explore these concepts a bit further so that at the end, you all will have a really strong idea of what these concepts are all about. So, first of all, let's just revisit a few key definitions. What is a system? What is the boundary? And what are surroundings? So a system is a region in space which is being analyzed in a thermodynamic point of view. It is nothing but a region in space which is being analyzed from a thermodynamic point of view. Now, a system can be any random demarcation. It need not be a specific object. It can include the region in space around the object as well. For example, if I am in a room, as I am here right now, and I want to analyze how much energy it would take to cool this room with me in it. So I have an air conditioning unit and I utilize my thermodynamic equations to try to compute how much heat energy I am giving off, how much heat energy is flowing into the room through the walls, windows, and so on and so forth. And then afterwards, I can compute this heat load analysis. So in this case, the entire room, inclusive of me, turned into the thermodynamic system. Then we look at the concept of the surroundings. Surroundings are nothing but the region in space outside the system. So everything other than that of the system is nothing but the surroundings. So you have the system, and everything outside is considered as the surroundings. The interface between the system and the surroundings is the boundary. Okay, so the boundary is sort of a imaginary wall which you encapsulate the system around, around which you draw around the system in question, and this encapsulates your entire system, and it is what that separates the system from the surroundings. Now, if you add these two concepts up, the system and the surroundings, you get something called a universe. So we have the system, you have the surroundings. What separates them? It is nothing but the boundary, and if you take them together, you get the universe. All right. So then after we look at classification of systems. So as we had looked at it earlier, we have three primary types of systems. You have an open system, a closed system, and an isolated system. Now, as in the figure on your screens, an open system is one in which you have both the red indicates energy and the blue indicates the transfer of mass. So you have both energy flow across the boundaries as well as mass flow across the boundaries. So say for example, as we had looked at it in the previous class, an example of an isolated system, an open system is if you are analyzing a section of a pipe. So if you're analyzing a section of a pipe, what it is nothing but an open system. So if you're analyzing this small section of a pipe, you have got mass flowing in, mass flowing out. Probably this pipe is not insulated, so you have got some amount of energy flowing in and some amount of energy flowing out as well. Okay, so this is nothing but a open system. A closed system is a system in which there is energy flow across the boundary. However, there is no exchange of mass across the boundary. For example, this water bottle. Okay, so in this case, as you can see, if I heat up this bottle, if I get a gas torch or something of that sort, or put it in a microwave, what's going to happen? The water inside is going to get quite warm. But however, the water will not be able to escape. All right. So in this case, this is an example of a closed system where there is exchange of energy. However, there is no exchange of matter. Then we will look at something called an isolated system. Now, an isolated system, there is neither an exchange of energy nor is there a exchange of matter across the boundary. An example of an isolated system is a flask. Probably you, as I mentioned in the last class, you probably use it to keep your soup warm or water warm, or probably use it to keep it cold. So what you do is you heat up the water, you pour it in the flask, and once you shut it down, you close it. What's going to happen is that the contents in the flask remain at the same temperature, or nearby the same temperature, whatever you had poured it in. So what's going to happen is that if you, after an hour or two, you'll still have that really hot water that you poured in earlier. Okay, so this is an example of an isolated system. Now let us go through a few more examples together so that you'll have a better and much more clear understanding of these kind of systems. And also in the interim, we'll be talking about a different kind of a system called an adiabatic system. All right. So let's look at each of the examples one by one together. Okay, so now here we have got three examples. We have got three examples of systems. One is we have got a flask here. You have got a flask here, and in case 1, a flask in case 2, and a flask in case 3. Now in case 1, what's happening is that you can there is some liquid inside the flask, and what's happening is that it's probably quite hot, and the vapors are going outside. Okay, so these vapors are going outside. At the same time, the flask is made out of glass, which is not exactly a great conductor of heat. But however, what's happening is that it's still not a perfect insulator. So there's some amount of heat interaction with the surroundings. Okay, all right. So now in this case, what is happening? There is mass flow across the boundary, as well as there is heat flow across the boundary. Okay, or energy flow across the boundary. So in case 1, we have something called an open system. Okay, as you can see, there is mass flow across the boundary, as well as there is energy or heat flow across the boundary. Now what we do is that we shut this entire flask from on the top, and what's going to happen is that that's going to prevent any of this vapor from escaping. Now what's going to happen is that since you've prevented the vapors from escaping, the mass which is inside this flask is going to remain trapped. It's going to remain trapped. So there is no longer any mass flow across the boundary. However, this flask is still the same, made out of the same glass, which is not a perfect insulator, and in this case, again, you still have some amount of heat interaction or energy interaction with regards to the surroundings. So this is an example of a closed system. All right. So you have got no mass flow across the boundary. However, there is energy flow across the boundary. Now in this case, the boundary in question is nothing but the edges of the flask. All right, so you can see that we consider that this edges of the flask is the boundary of the system. Okay, now see in this next example, what we do is that we add a layer of insulation. We add this orange color insulation to the surroundings of this closed flask. We wrap this entire flask in a thick layer of insulation. Now what's the insulation going to do? It's going to prevent the transfer of heat either from outside to inside or inside to outside. So right now in the third example, in the third case, we have neither energy flow nor neither mass flow, nor do we have any energy or heat flow across the boundary. So this is an example of an isolated system. Okay, so we have an open system, a closed system, and an isolated system. And note that just by doing some small modifications, just by putting a stopcock on the top, all right, we converted the open system to a closed system, and just by wrapping it out, the closed system with a blanket or something or some insulating material, we converted the closed system to an isolated system. So just because you have a setup, it does not give us a clear definition of what the final type of system may be. They can transform from one system to the other. Okay, so please keep that in mind. Just analyze the system from a thermodynamic perspective, and I'm sure that you will be able to understand what the concept of a system may be. So let us have a look at a few more examples so that you all completely and thoroughly understand what or know how to classify into what kind of a system we are talking about. So let us look at an example. This is a rocket engine. Okay, now you can see there's a lot of complex plumbing which is going on here in this region of the rocket. In this region of the rocket is a lot of complex plumbing going on here, and this is the nozzle end of the rocket, the business end of the rocket, and you can see really hot gases flowing out of the nozzle end. Now let us analyze this as a entire system. Okay, so let us consider this bit as our system boundaries. Okay, this bit, and you can see I've just marked it in red here. Of course, let's try to get a bit more color here. Just a second. Let's get purple here. I hope this is a lot more visible than the previous color. All right. Okay, so this is our system. Okay, now the purple obviously represents the boundary, and whatever is outside the system is your surroundings. So now you have the system, you have the surroundings, as well as the boundary. Okay, so now in this problem, what you have is you have got the rocket fuel flowing into the engine. You can see this arrow which I'm trying to draw here. So you have got rocket fuel and the oxygen which is also flowing into the engine. Okay. What is happening is that there is combustion taking place inside the engine, and all of this hot exhaust is being thrown out at really, really high speeds. Okay. So in this problem, you have got mass flowing into the system. You have got mass flowing out of the system. Mass in, mass out. At the same time, what's happening is that this entire nozzle is turning red hot, as you can see from the image. And once it starts turning red hot, it radiates heat to the surroundings. So there it is transferring the thermal energy to the surroundings by means of radiation. Okay, so it is transferring this heat to the surroundings. So in this example, your system has mass flow across the boundary as well as energy flow or heat flow across the boundary. So this is nothing but an example of an open system. Okay, so this is an example of an open system. Okay, I hope that you have understood this example. Just to make sure that you understand what an open system is, let's look at another example. So we have a car engine. Okay, so from some device which takes us to the stars to something that really gets us around in our day-to-day world. Now this is an example of a high-powered engine. This is a BMW engine which is used in F1 cars. Okay, I really hope that you like the sport. It's a wonderful sport which really excites me, and It is one of the cutting edges in technology, and it's really amazing to watch as well. So anyways, this is the power plant of one of those F1 cars, and you can see this mess of tubes which are taking the exhaust gases from the engine to the exhaust port. So it's routing all of this engine exhaust from the engine to the atmosphere. Now let us analyze this engine. Let us analyze this engine inclusive of this. I'll get a red color marker here. So inclusive of these red hot pipes. Okay. All right. So this box encapsulates our engine. So this box is our boundary that we have assigned to the system. Okay. So now the engine turns into our system. Okay. So we are analyzing the engine. Now, in this case, you can see these pipes which are coming from the top. These are bringing in air and fuel into the engine. Okay, so there's mass flow into the engine. At the same time, through the exhaust pipes, you have got mass flow, that is your spent gases, your exhaust gases, which are flowing out. So you've got mass coming in, you have got mass going out. At the same time, these red hot pipes, they are radiating all of this heat, they're radiating all of this thermal energy, and they are dissipating this thermal energy to the atmosphere or to the surroundings. So in this problem, you have got mass flow across the boundary as well as energy flow across the boundary. And this thus is an example of an open system. Okay, so this too is an example of an open system. I hope you are understanding this. Let us look at a few more examples. So now this is probably a bit more a slightly different problem. So this is an example of a water cooling system, which is found in a lot of gaming computers or any high powered computing device. Now they have introduced a few RGB elements, that is RGB lighting elements, and it gives this really wickedly cool color or coloring scheme. Okay, now what a RGB, sorry, not an RGB, what does a water cooling system do? So what happens is that your CPU, the central processing unit of your computer, even though it does a lot of these operations and it is remarkably efficient, what happens is that all of this electrical energy which you're putting in gets converted into heat energy. There's a lot of thermal energy output which is there, and this needs to be dissipated. If not, there's going to be thermal failure. So in most of the systems, including that of your phone, including that of your laptops, it's just mostly passive dissipation. So what is happening is that the surroundings get warmed up, and then after by means of conduction or convection, it is just spread out into the atmosphere. But the moment you start having desktop class systems, or even higher end laptops, what happens is that this passive cooling cannot it does not provide enough adequate cooling. So what you have to do is you have to do some bit of active cooling. You probably have a fan. However, in really high end systems, what happens, even this fan cannot provide enough cooling. So what do? You provide something called a water block, and this is the block which you can see here. You can see the water block here, and what it does is that water block is in physical contact with the actual CPU. So it's a body of copper which is in physical contact with the CPU, and within this body of copper, there are pipes. There are internal pipes which are built, and through which water flows. So as soon as the copper gets hot, the heat is transferred to the water, and the water is carried away. Okay, through this entire cooling loop. And it passes to a massive radiator which dumps the heat into the atmosphere. You can see these radiating fans. Okay, so they dump into this atmosphere, and then the water returns to the cooler to a sort of a storage tank, a reservoir it's called, and then after it returns to the water, to the entire the CPU, the thermal block. Okay, so the water is passing through this closed loop, and I'm pretty sure you understand where I'm going. So let us analyze this cooling system as a whole. Okay, now the water is passing through one component of the cooling system to another component of the cooling system to a third and back again. So it's looping around. There's a continuous loop of water. However, you probably don't want this water to exit the system. In this case, the water does not go out of the system. If it did, your entire system would probably not really be in the best of conditions anymore. Okay, so in this case, water just travels from one component of this entire system to the other. However, it remains within the system itself. So within the water cooling loop, it just is it's only there. It does not go out of the system. So obviously, there is no mass flow across the boundary. Okay, so in this example, there is no mass flow across the boundary. However, that does not mean there is no energy flow. We try to extract the heat from the CPU and then we pass it into the radiator where it is dumped into the atmosphere. So there's energy coming in and there's energy going out. Energy coming in and energy going out. Okay, so this is an example of a closed system where there is no mass flow across the boundary. However, there is energy flow across the boundary. So this is an example of a closed system. Now, if you had the system at home, I'm pretty sure that you would have a real blast. Imagine if you had a dog and they decided to push the system. It falls down, the pipes break, and what's going to happen? This closed system is soon going to be turned into an open system. I really hope that this never happens to any soul, but yeah, this is a possibility. So your closed system can turn into an open system. Going ahead, let us look at a fridge. Okay, now looking at the fridge, what I'm going to talk about is a really important new concept. Okay, so in a fridge, what's happening is that, say if we put really some warm liquid inside, what do you want at the end of it? You want your liquid to be cool. So what's happening is once you close the doors of the fridge, there is no longer mass flow across the boundary. Okay, so whatever the content inside the fridge is, it is going to be sealed. Yes, am I right? Now what's going to happen is that if this entire content is going to be sealed, there's no mass flow across the boundary. Zero mass flow. However, there is energy flow. Again, how? So in this case, what is happening is that you supply electrical energy to the system. You supply, let me just change the color. So you supply electrical energy to the system. Okay. Now this electrical energy is nothing but it does nothing but electrical work. Okay. At the same time, what's happening is that the entire compressor is doing work. It's converting this electrical energy into thermal energy, and it's trying to extract heat energy from this your cold drink. And what it's doing is that it is taking this electrical energy and converting into some form of heat energy, and it's dumping the net amount of heat energy out of the system. So there is no mass flow, but there is energy flow. So this is an example of a closed system. Okay. However, imagine if this was a heater. Imagine if this was a heater, a furnace of sorts. So in that case, what you wanted to do is you wanted to heat this, the liquid or whatever you wanted up. Okay. So in this case, the entire system would still be insulated because you don't want any heat loss. Sorry about that. You want this entire system to be insulated, so there is not any heat loss. Okay, so this system is now insulated. At the same time, you have got some amount of electrical energy flow. So this electrical energy inside is being used to heat up this entire substance. Okay, it's used to heat up this entire substance. Now, thus, there is electrical energy, that is electrical work, which is flowing across the boundary. However, there is no energy flow which is coming out of the boundary. That in terms of this heat loss, that is now zero. The heat loss to the surroundings is now zero. Why is the heat loss to the surroundings zero? It is because you have placed this insulation. Okay, so in this case you still have electricity flowing into the system. However, there is no heat flow out of the system or into the system. Do you understand? There is energy flow, that in terms of electrical energy, there's electrical work being done into the system. However, there is no heat flow across the boundary. Okay, this kind of system is no longer a closed system. This is something called an adiabatic system. An adiabatic system is a system in which there is no mass flow across the boundary and no heat flow across the boundary. In an isolated system, there is no energy flow across the boundary. In an adiabatic system, there is no heat flow across the boundary. Please understand this really important distinction. Okay, in an adiabatic system, there is no heat flow across the boundary. In an isolated system, there is no energy flow across the boundary. Okay, this is an example, or this is a sort of an example in which you convert an open system to an isolated system. Okay, so this is nothing but a thermoflask. This is nothing but a thermoflask, and this is a special kind of a thermoflask. What is pouring out of it is nothing but liquid nitrogen. So there's liquid nitrogen which is pouring out of this thermoflask. All right. Now, if there's liquid nitrogen flowing out of the thermoflask, you probably would understand that the contents are really cold. Yes. Now, if you close this thermoflask, what's going to happen is that the liquid nitrogen is still trapped inside. Liquid nitrogen is still trapped inside. Okay, and liquid nitrogen is really cold. It's nearly so liquid nitrogen is or nitrogen is liquefied at minus 160 degrees Celsius. I'm pretty sure you don't want to touch that liquid which is flowing out. So if you close this shut, what's going to happen is that the liquid nitrogen is trapped inside. Now this liquid nitrogen is at what temperature? As I've just said, it is at temperatures lower than minus 160 degrees Celsius. Now if you look at this image at the side, you can see this man holding the flask, okay, with his bare hands. If there's something that cold, would you want to hold it? No. So what this flask is doing, it is insulating the liquid nitrogen from the surroundings and the human being once closes. Okay, so if you close this liquid flask, what is happening? There is no mass flow across the boundary. At the same time, there is no energy flow. Okay, so there is no mass flow and there is no energy flow across the boundary. So this is an example of an isolated system. Okay, this flask, not this flask. Once you open it up and you can see the liquid nitrogen pouring out, it turns into an open system. Okay. All right. I hope with this example, you understand the concept of what a system is, what the boundary is, what the surrounding is, what the universe is, and how to identify each of these systems. Okay. Now, let us look at a sort of a combination of these different systems. In the image, you see a rocket going into space. Okay, it's traveling upwards, and you can see this really amazing cloud sort of formation which is happening in this region. Okay, so this is funnily an example of different types of systems that are put together. Okay, so the engine, as we mentioned, they are open systems. Now, this rocket is broken up into different segments. So this is your first stage. This is your second stage. And this bit till here is your third stage. Okay, so the first stage is currently operating. It is currently operating. So what's happening is that there is mass flow, okay, and as well as there's obviously energy flow across the boundary. So it's an open system. The second stage contains the fuel in this rocket is liquid hydrogen and liquid oxygen. O2. This is O2. So oxygen is liquefied at temperatures below 90 degrees Celsius, and hydrogen is liquefied at temperatures below minus 153 degrees Celsius, 253 degrees Celsius. So clearly, you need to keep the contents of this rocket stage really, really cold. Okay, so this entire system right now, since it's not operational, everything is shut down, all of that. There is obviously no mass flow across the boundary. At the same time, since you need to keep this the liquid hydrogen and liquid oxygen at really low temperatures, there's no energy flow across the boundary as well to heat this entire liquid nitrogen and liquid oxygen up. So this is an example of an isolated system. Okay, same thing for the third stage. All right, so here you can see in this example, you have got an open system, you have got an isolated system. Okay, at the same time, if you look at this at the top, if you look at the top here, this is where the humans sit. Okay, so that bit is called the capsule. Okay, now inside the capsule there is it's sort of a triangular shape. They are the humans inside. Here there is your breathable air, and you do not want it to escape. So obviously you seal this entire, you do not want it to escape. So you seal this entire capsule really, really well. Okay, so it is closed. At the same time, you want all sorts of the communication, all of the controls for all of these rocket stages, you want all of that to pass through. At the same time, to operate the controls, you need energy and you need that to pass through. So this is an example where no mass is flowing across the boundary, but there is interaction of energy across the boundary. So this capsule is an example of a closed system. Okay, so in this rocket, you have an open system, an isolated system, a closed system. Okay, so with this, I will bring this session to an end, and I really hope that you have understood the concept of an open system, a closed system, an isolated system, an adiabatic system. Now, when I want you all to go outside, when I want you to look outside, I want you to figure out a few more examples of each of these cases. Okay, so look out for open systems, isolated systems, closed systems, and try to figure out how they play or how they interact from a thermodynamic perspective. With this, we will bring this session to a close.